Oh, there we go. Okay, so I'm Mike Houston. I lead the deep learning team at NVIDIA. So my team works on our tools for training, the platforms that we build. I'll talk about a few of them. A lot of technologies behind deep learning, new algorithms. We have a fairly large team. So I'm going to kind of very quickly go through how deep learning works and its applications to automotive. So this will be awfully fast because I want to show you guys a bunch of things. Okay, so where's deep learning generally used? So it's used in lots of fields. So it's perhaps best known for image classification. This is like the ImageNet contest. I'll talk a little bit more about that later. But object detection, localization, action recognition, scene understanding. Lots of stuff on speech now. So if you've ever interacted with many modern voice recognition systems, there's deep learning backing those now. Same thing, things that understand and translate text, a lot of those are moving towards neural networks now. Specifically for automotive, pedestrian detection, traffic sign recognition, free space calculations. There's lots of things that rely on deep learning. And then there's a bunch of things in the medical space, specifically as of late, detecting cancer cell mitosis, analyzing brain scans, things like that to try to accelerate care. Okay, so what is deep learning in a nutshell? Well, I'm going to concentrate on what we call convolutional neural networks. So these are sort of the modern style neural networks that most people use. So the best way to think about it, it's a stack of layers. Each layer is going to calculate some combined value, and it's going to pass it via a connection to the next layer, okay, as we go all the way through. So if you think about what the representation internally is in a neural network, it's basically learning a hierarchy of features. So the first layers, if you're dealing with images, generally build things that are referred to as Gabor filters. So things that are sensitive to gradients, textures, colors. So very similar to how your retina and your optic nerve behave. That's what it's modeled after. So as you go deeper in the network, it begins to piece things together. So in the case of recognizing faces, you'll get things that look like eyes and nose and mouths and different styles of those. And then at the output, it'll basically start understanding how to piece those together to recognize different people, right? So this is how most basic face recognition systems using neural networks work. Now, there's lots of details about how to make a production system, but this just gives you a view of how they work. So how do you train these things? So here's an example from ImageNet. This is sort of now the hello world, if you will, of convolutional neural networks. So I'm going to take a bunch of images, trees, cats, dogs, let's say, as my initial thing. I'm going to randomly initialize all the weights in the network, and then I'm going to attempt to learn how to differentiate these images. So I'm going to take the dog, I put it through the network. It's called forward propagation. And because it was randomly initialized, it'll say, hey, that's a turtle. Well, it's not a turtle. So what we're going to do is we're going to compute what the distance was from the correct answer, and we're going to nudge the network a little bit in that direction, and then we're going to propagate those results all the way back. That's called back propagation. We're going to repeat this. I'll only show 3 images here. In practice, you're going to repeat this millions of times on millions of examples of images, and the network's going to learn. So lots of repetition. From this, you get a trained neural network model, which you can then deploy and then do what we call inference, so forward pass only. So I can take in my picture of my cat. It's actually one of my coworker's cats, and it'll say cat. And if you actually try this with ImageNet for real, this is actually exactly what will happen. So training and inference phase. So an example of it, you'll see the demo later, although Tim's going to have to rerun it because our memory leak came up again, as usual. That's why you don't put that in a car yet. So what we did is we stuck GoPros in cars. We ran around. We gathered a whole bunch of data. Okay? Then you have to tag that data, right? This is what's called supervised learning. So we used good old Mechanical Turk. We wrote this fancy script so that we had humans go around and label all our things. And we used a complex cross-voting scheme. If you want to talk about it later, I can. So we tagged things like pickup trucks, SUVs. Our main concentration was to actually differentiate special use case vehicles. So emergency vehicles, school buses, right? That's what we're attempting to do. So we gathered a bunch of data, and then we did a training phase. The screenshot you see here is from our tool called Digits. We'll talk about it a little bit later. But you see a training run over time. So at the time, this took 16 hours to do. On a machine I'll talk about a little bit later, we can do it in 47 minutes now. Very, very fast to train this. Now, this is not production-capable network. This represents 40 hours of data, and we had 68,000 tagged objects that we used as our training set. So good enough for a demo, not for production. So let me give you kind of a quick example of that, and you guys can see the demo a little bit later. So what we do is we use a scanning window detector to find regions of interest, so lots of false positives, and then we hand those to a neural network, which filters them all out. So we get the boxes and then what's in the box. It was trained on 40 hours of video only, as I said, so it'll mess up occasionally. The point is how rapidly you can actually get something that actually works pretty well with deep learning, compared to trying to hand-tune all this stuff with traditional computer vision approaches. So deep learning sort of existed in the 90s and then disappeared, and now it's back. Okay, what happened? A couple of things happened. There were large improvements in the algorithms. So most notably, how the activation functions worked. So there was an invention called ReLU. So it's a nonlinear activation function, which solves some of the instability problems in training the network. And there were other improvements to the backpropagation algorithm. Alex Kryashevsky, who is now at Google, wrote sort of the seminal paper that sort of jump-started everything. So, and what was it about his paper? So he figured out how to make use of tremendous computational density in the case of GPUs. So things that used to be impractical to train, that used to take years to train, where he was able to train in weeks, right? It changed the nature of what we could take on doing. The other thing is the explosion of data, especially images for visual tasks. It used to be very difficult to get enough images. Now we're drowning in images, right? So you combine improved algorithms, a tremendous amount of data, and tremendous computational horsepower, and it makes deep learning viable. So I talked about some of these medical research things. I'll skip over this. It'll be in the slides. But it's amazing. Now we have this big, giant hammer we walk around with. It's amazing what you can apply it to and make things work really, really well. So there's actually a good paper written by Andrei Karpathy at Stanford on the unreasonable effectiveness of recurrent neural networks, sort of the ultra-modern, state-of-the-art version of neural networks, and how they work amazingly well on very, very difficult tasks. So his work, one of these examples, is captioning. So besides saying, hey, that's a bird, it's actually gaining deeper understanding of the system. So it's a bird perched on a branch of a tree. Right? That's a fairly hard concept for a computer to usually deal with, but it's actually proven to be pretty successful. So you've seen, if you search around the web, there's lots of examples of this now.
Can you tell the person's name again at Google who wrote the paper?
Alex Kryashevsky.
Do you have any sense of his spelling?
I can't do that off the top of my head. It starts with a K. K-R-I-E.
What should I search on?
If you search for AlexNet, AlexNet.
E-L-X.
A-L-X-A-L-E-X-N-E-T. You'll see a slide on a second. Okay, so why are GPUs good for deep learning? So neural networks, specifically convolutional neural networks, are inherently parallel. They effectively break down to matrix operations, so convolutions, and they have lots and lots of floating point operations required. Well, this is one-to-one with what GPUs are good at, right? GPUs are the highest density, generally programmable floating point engines on the planet. So there was this huge pop that happened when Alex published his work in 2012. You went from everybody using traditional computer vision to basically everyone using GPUs. There's only one entry that did not use GPUs, but they were using neural nets in the last contest. The other thing is we've actually passed human reference for ImageNet. So the accuracy is now believed to be higher than the natural error in the data set. Now, to be fair, only one person did this, and it was Andre. He sat down and became the human reference to train himself how to do these things. So he represents the human reference, right? Grad students, I mean, I'm glad he suffered. He suffered for his craft, right? But there's been this sort of massive shift. So this is sort of this takeoff now that's happened. So, and lots of people are using deep learning. So here's all the companies that have talked publicly at GTC or other places that are heavily engaged in deep learning. And basically everybody on here is using GPUs to do it, at least on the training side.
What domain are they using? It's all automotive? Like what
No, so it's all over the place. So actually very few of these are specifically automotive. I'll talk about some of the automotive companies and show examples. Most of the companies here are doing various things on imaging. There's a lot of folks doing speech recognition. Some people are doing data mining, right? It's sort of all over the map. Again, deep learning is sort of a big, giant hammer. All right, you throw data at it, you try a bunch of different models, and you'll inevitably find something that fits. We can talk offline much more about some of the problems with that, like overfitting your data, which is one of the tricks to avoid when training this. So for those that want to sort of know where to start, here are the major frameworks that are used. There's more on here. Don't be offended if it isn't on here. These are just the ones that seem to have the largest user communities and the largest number of active check-ins on GitHub. So you have Caffe from Berkeley, Torch, Theano, CUDA ConvNet 2, which is Alex Kraszewski's work, and Caldi. So Caldi is a speech recognition framework that's public, that's on here.
Which one would you recommend for a starter?
So so the question was, which one do you recommend for starting? It really depends, honestly, on what you're most comfortable with. My team, we heavily use Caffe. So Caffe is a C++, fully oriented system. Its advantage is C++, the code's reasonably well hardened. It can be daunting to implement a new algorithm in Caffe. You have to be pretty comfortable with the framework and C++. Torch is C++ backed, but you actually interact with it with Lua, which is a scripting language, so it can be very rapid for research development and deployment. Theano is Python, and it's very mathematically focused. You express things mathematically all the way through Theano. So you come from a math background, you may find that the most compelling. CUDA ConvNet 2 is, well, it used to be the fastest. Now, actually, the work that we've done with Caffe, Torch, and Theano, those can actually be faster. Now we have an optimized library called cuDNN. But CUDA ConvNet 2 right now has the best multi-GPU performance. Although we've been working with Flickr, and there's a pull request in the Caffe branch, and there's also work we've done with the Torch team for multi-GPU support. But Alex's code is still faster.
A quick question. How does Adam from Microsoft or Watson fit into this framework, or they're completely different?
So Adam and Watson are different beasts. So they also rely on machine learning, but these are all heavily related to neural networks, where Watson, Adam, there's a bunch of other approaches, also use other machine learning techniques. Sometimes it's graph analytics. Sometimes it's restricted Boltzmann's machines. There's lots of other types of machine learning beyond deep learning, or what we refer to as deep learning. All right, so let me quickly talk about the tool that we use. So when we were doing that demo, we had to deal with very quickly training networks and managing a lot of data. So we developed a tool called Digits. So it's open source, BSD license. If you Google Digits, you can find it on GitHub. So it's designed to process your data, help you configure design DNNs, analyze the DNNs, monitor progress of training sessions. Right now it supports Caffe primarily, although there's a Torch pull request for full Torch support behind Caffe as well. And it runs GPU, multi-GPU, and we hope to extend to GPU cluster and cloud support. And there's pull requests coming in from startups to do that. So here sort of looks like visually. So you can process all your data. You can pull things from web-backed resources, local NAS, files, whatever. You can configure your DNN, so you can, AlexNet, GoogleNet are sort of the defaults in there, as well as Linnet, which is used for MNIST, this character recognition. You can start your training session, monitor progress, right? So the blue curve is how your accuracy on this particular test was going. The other curves are your loss rate. We can talk much more if folks are interested when you train things. The key thing I'll tell you is if you see your validation loss and your training loss diverge, you're overfitting and you're going to be unhappy and sad. If you see it jittering all around, you're underfitting, you are unhappy and sad. So the reason we developed this tool is it's not just, when people ask me, well, what network should I use? It's not really that simple of a question. You just can't use AlexNet and it solves, the world hunger problems. You have to start with these networks and you kind of poke and tweak and you kind of see how it behaves and you kind of morph it into what you need. And AlexNet is really set up for classification, although if you read the papers, it's still the workhorse for localization and it's still where people really start. It's a comfortable, well-understood network model. And then we can visualize the layers so you can see how your network's reacting. The newest version of Digits actually has a bunch of statistical analysis of your activations to help you sort of understand what's happening in your neural network. So this tool lets you push a button and process all your data. It doesn't let you push a button and get the optimal network. Okay? This is designed for data scientists to process things. We also built a specialized box to do this. So we suffered doing that demo, meaning, demos are demos, so we're running out of time. We needed the fastest thing we could build. So we spent time to actually build a heavily optimized box. Okay? I'm not saying go off and buy this. I'm just saying if you want the fastest box you can buy with all the software set up, you can buy this if you want. Okay? Very fast. This is what our team uses literally for our work. We just decided to sell it.
Amazon AWS also has your GPU cloud.
So AWS has our GPUs. They're a generation behind what's in this system and significantly slower. But it's a very good place to start. The main issue on Amazon right now is the available disk space for your data set, right? The SSDs on the G2 instances are only 60 gigabytes. If you go to an 8x large instead of the 2x large, that quadruples. And you can get access to 4 GPUs. But each of the GPUs has smaller amounts of memory and are generally slower. The GPU that's in that is more than twice as fast as the GPU in AWS.
When they will upgrade to this?
You'll have to talk to Amazon about when to upgrade to newer GPUs. All right, so let's talk about automotive. Here's sort of the best way to think about how sensors are placed and how modern ADAS works. It's usually some combination of these things. So not many things actually rely on optical. There are systems shipping today that are heavily optical driven. Most systems shipping today, though, are radar and ultrasonic is how they deal with things, right? So adaptive cruise control type things, right? The main goal of modern ADAS is don't hit the thing in front of you, right? Is the best way to sort of say about it. And that's an excellent start to things. But the other problem with this is if you look at all the equipment that's going on in these cars, and I'm not including LiDAR here. LiDAR is too expensive currently for most production vehicles. It's very expensive to put, say that again?
Are more accurate?
So LiDAR is a different technology. So LiDAR can be more accurate. So if you buy the nice $10,000 Velodyne, that thing is sweet, right? It still has noise in it, but it's 10 grand, right? You can buy a pretty nice car on eBay for 10 grand, right? So, and in the end, what you'll find is even with your nice fancy Velodyne, you'll end up still needing the other sensors. So you can easily end up putting 50 grand of equipment on your car, right? If you're trying to target a $30,000 car market, you've started in the wrong place, okay? So, again, prove everything out with LiDAR. I'm not going to argue, about that. Totally the right thing to do. Any test vehicle that we would have, I'm putting LiDAR on it, right? You get more data. More data, good. When you get to production vehicles, you need to figure out how to do it better, cheaper. So, the way that sort of we think about it, and I think the industry as a whole is beginning to think about it, is progressively replacing more and more things with optical and keeping secondary sensors or primary sensors, depending on how it fits in your pipeline. So forward-facing radar. My gut is you're not getting rid of forward-facing radar. You're going to fuse it with multifocal optical systems. Notice I didn't say stereo, multifocal, so different focal lengths, so you get resolution at different lengths, distance away from you. And you fuse those together to get a very robust system. So optical will fail in fog. We'll use a radar system. Radar will fail with weird metallic objects. So God forbid a chip bag flies up in front of your car, right? It looks like this huge object to the radar system, but your optical system knows it's not. It's not a truck, right? So you can combine those things together. But we can also begin to get rid of a lot of car manufacturers don't like, they refer to them as warts of the ultrasonics, the little circles you see around the car. So we can switch to camera-based systems. For that, it helps a lot. It also begins to reduce the cost, right? Consumer cameras are getting really, really cheap. You don't need ultra-high-end cameras to do sort of your surround vision type work. So I'm not going to harp on this a whole lot because I'm an engineer and not a sales guy, but we develop a board, and that's what's designed to run these demos, and this is what we use. So we designed a board that has 2 of our high-end TEGRA chips on it. It can support 12 cameras. The board that's over there has an FPGA on it as well. We already have FPGA algorithms, safety critical systems that can run on that. But this is designed to be a camera monster and still take in radar and ultrasonics and all that stuff, and run state-of-the-art computer vision and state-of-the-art neural network technologies. So let me show you one. So this is brand new this week. There's a startup called ADASWorks, spun out of Captioning. So this is running 4 cameras on a single X1, one chip on that board that I showed. They're doing lane detection, car detection, blind spot analysis. That's what's up front. The red bars mean they're blocking off lanes, that there's something in that lane. It's not quite running, at full speed yet. They haven't finished tuning, but it shows what this platform is capable of. So this is traditional. This is all traditional computer vision, right? And you're still going to see traditional computer vision on cars moving forward. But building just base detectors doesn't lead you to a self-driving car. You need much more understanding about the world. Another way to say that is a pure computer vision system is a reactive system. So it can be a little daunting if you're in that car because it stops and starts and judders because it's just reacting to everything, as opposed to a better understanding of the world and being proactive about what it sees. So if we talk about sort of the DNN side, so how fast can X1 be? So if you take AlexNet and you tune the heck out of it for inference, how fast can we do inference? We can do it 90 frames per second, okay? So AlexNet takes in a 227 by 227 image. So this isn't, again, you don't take AlexNet and self-driving car. It doesn't work that way. But AlexNet is a good standard for the size of networks that you can run and what you're capable of processing. Remember, as I said, AlexNet is sort of the starting workhorse still of a lot of algorithms. Some people might argue GuggleNet and VGG, which are sort of more modern, fancier networks, which we also use. But to be blunt, we all start with AlexNet still.
So is 227 good enough for forward-facing?
So 227 is good enough for the classification task. As you get for detection, what happens is you move to these more advanced networks, which we'll talk about in a little bit, where you basically do scanning window inside the network, not externally. It's more efficient, and then we can scan the whole video frame and then tag the objects. All right, so let's talk about today's ADAS. This shouldn't really surprise anybody. So usually do you use sensing on an FPGA or specialty computer vision ASIC. You're planning on a CPU, and then basic systems today, you basically warn, so loud beeping noise to try to get your attention, which tends to be over-conservative because you need to react. So if you've ever sat in some taxi cabs that have some of the aftermarket vision systems, they beep and it drives the taxi drivers crazy. It has to be overly aggressive because it has to get your attention and then wait for you to respond, right? That's just how the systems work today. So it can feel that they're overly aggressive, but they're doing what they're supposed to do, okay?
What's that, a half-second cycle?
So you can debate. Most people tell you it takes a human a quarter of a second to react.
What does ADS stand for?
ADAS, Advanced Driver Assistance System.
It would be great if you could repeat the question.
Okay, I'll try to get better at that. Okay, and then as you move into sort of next generation ADAS, so lots of people are starting to do free space calculation, as are we. And so this is where you begin to get a little bit more advanced, right? So you may take on steering, so lane change, right? So especially like highway lane change, right? Relies on this technology. And sort of that is what I showed you. So if you know everything around you and you know which lanes are open, you begin making lane change decisions. It also means instead of just braking, you begin now making acceleration decisions. So adjusting speed fully autonomously, handling overtaking. We're not very far away from seeing that in production.
Just FPGA, CV, ASIC, this is custom that the car manufacturer does, or this is what you supply to the car manufacturer?
So the question was, FPGA, CV, ASIC, does the car manufacturer do that? Do we supply it? So the boards, we have boards that have FPGAs on them for people that already have their own algorithms. There are other companies, most notably Mobileye, that develop a custom CV ASIC. Okay? Okay, so where do we envision that sort of deep learning works into this? Deep learning is basically an extension, enhancement of the system. So if you look at, again, what happened in ImageNet, nobody uses traditional computer vision on ImageNet anymore. And there's a reason why. It's sort of tapped out, right? And where there's this huge shift as we took on machine learning algorithms to do this, or deep learning algorithms to do this. So what's the big difference? Why do you need a DNN? So a DNN is able, remember if we go back to the captioning thing where it can say it's a bird on a tree, a DNN is able to provide more context to the scene, okay? A good example is if there's a school bus and it doesn't have its lights flashing with a stop sign out, you get to drive by it. If it actually has that information, your free space calculation is now drastically different, right? You're not allowed to pass. You need to know that information. You say, it's an easy one. I can detect the stop sign. Okay. Try to detect somebody opening a door. You and I see it, right? We see that door crack open, and we know, I'm going to give that person a little bit of room, and I'm going to move to the left, okay? These are very hard. Trying to develop a computer vision algorithm that can detect that, while possible, is awfully daunting to try to take on. Hand tweaking, feature detector to do that. These are things that can be done in a deep learning system. So if you go one step further, right, you don't get, remember what I say, you don't get an autonomous car by just kind of adding detectors upon detectors. I can't build a custom detector for everything in the world. And you don't train somebody to drive that way. Like you don't teach your teenager Newtonian physics to drive a car, right? You sort of teach them the basics. Here's a stop sign, don't hit this. If they're learning clutch like I did, try to stall a car out. So the way that we think about this is a little bit different. So we hired Urs Mueller, who worked on the original Dave project. And so in some ways, some people may call us a moonshot project for deep learning. I actually think this is a very realistic way to approach deep learning. So what this says is assume you have sort of all the basic don't hit stuff technology, so your CV ASICs, your basic planning. Can we actually teach a robot or a car how to drive itself based purely on watching a human drive? So steering inputs, left, right, accelerate, brake. Okay? So let me describe the training data, and then I'll show you the results. Okay? So what the training data looks like is it's supervised learning still, but it's very easy to get this data. So I'm going to show you the remote control car version of things. So we give these pictures, and so a human is sitting there with remote control, and in the case of this where it sees a wall, the human's going to turn to the right. right? And the general rule here is stay 3 feet away from an object. That was what the human was told to do. So the question is can the robot actually learn to replicate the human driver accurately, and can it drive on a scene it's never seen before that's very difficult? So here's our little Dave robot, and we're going to drive in a backyard. There's no human driving. It's purely a computer, so you'll see it weave a little bit. But it's able to path plan through pretty complex environments and not hit stuff. Like it goes around that pole, right? It heads off through the fence and the gate. And it's never seen this before. It's just making decisions based on what it's seen from a human. Okay? So down this alley, I mean, it's pretty impressive that we can pull this type of stuff off, right? And again, all that we had here was a picture and effectively what the actuator in the car was doing at that time. So the cool thing is, we get this off of vehicles. You put cameras in a vehicle and you attach the CAN bus, what do you get? Brake, steering angle, acceleration, speed, right? You get all the information to begin training these things. So this is the path one of the paths that we're beginning to head down. So why else is deep learning cool? So if you bake an ASIC for traditional computer vision, how do you update it or deal with faults in the field? Question.
So the past training data, was that someone driving the car around, or is that someone actually like car?
No. So the training data for the RC car, what was it? No, it was we were recording somebody holding the remote controller doing it. It wasn't car data. So that's a derivative of AlexNet, and there was only 225,000 input images, so that was pretty quick. That was less than a day to train that one. So why is deep learning kind of cool? Well, because we can do active learning. So we can actually improve things in OTA vehicles. So what's cool about this is it means that nothing is ever going to be perfect. There's always going to be these weird exceptional cases. So what would be an exceptional case that we'd want to improve our training on? Well, we actually get a confidence metric out of the neural network. So if the confidence value is low, we can be concerned, and we can take that as input data, go back up to the cloud, into the data set, train, retest that, split into validation, training, test sets, train on it, and then OTA vehicles. So if you can do this really, really fast, it means that we can potentially handle things like construction zones. Construction zone, the car has no idea what to do, relinquishes control to the user. 10 users do it. Upload that up. The next cars that come through have the uploaded, can navigate through road changes. Right? It's an interesting question of how fast you can train, how fast you can validate, how fast you can go out. It's not going to be minutes, But if you get a bridge change or a lane closure that's let's say days, maybe we can do this fast enough. Question.
When you add that training, would the previous training get kind of messed up?
So when you add that training, would the previous training get messed up? So no. And there's multiple ways to do that. So you can supplement your current data set, or you can do what's sometimes referred to as fine-tuning, meaning that you can actually lock certain parts of your neural network so they don't move, and you're basically trying to tweak the objective function in a certain direction. So there's multiple ways to do it. In the end, if you're really, if you have thousands of cars out there and you're getting lots of data, what would happen is you'd be continuously retraining through your system all the way through.
Another question. I'm just wondering if you look a little forward, like long time back when the cars were first on the road, you never had, when you brake, the
no brake lights.
Come up. So I was wondering, like say 10 years out, what kind of sensors do you want every car to have so that, see, all the work is being done on the system, assuming we're not getting signals from the guy. So what would you like to see? Right,
so excellent question. So we're doing all of this, I'm just going to summarize and say, we're doing all this the hard way, assuming that the cars aren't talking to each other or we don't have communication infrastructure. Right, autonomous cars. So we have a couple of problems, right, in practicality. You have legacy vehicles, right? It can take 20 years to replace legacy vehicles unless there's some forcing function. So you have to do the hard stuff, unfortunately. If I had sensors, there's a tremendous amount that would make my life much easier. So path planning. I'm making it really hard to find lanes. If we just did something as simple as embed RFID tags in the road that told me my location as I passed over them, it would make life much easier for me. Instead of trying to detect brake lights, and there are like mining trucks that are automated that do this. If the guy braking says, hey, I'm braking to the guy behind, then it's a nice smooth thing, and you can build high density convoys. I don't know if people saw the Mercedes truck, right? The Freightliner. It actually does this. So you can go into convoy mode, so you can link the trucks up, and then the trucks actually now communicate. So the first truck now takes piloting over for an entire convoy. Pretty cool idea. And they rely on cab-to-cab communication there. It's automated. So I mean, they can come to an emergency stop altogether flawlessly, inches from each other. And it's because of that. If you're relying on vision systems and everything else, there is latency. Where if you're sending a signal saying, I'm issuing an emergency stop, then everybody just does it. Right? It can be done in sub-millisecond, as opposed to waiting for a vision system, which let's just say is 30 frames per second, so 16 milliseconds to react. Still way faster than a human, but yes, if we had communication to other vehicles and we had communication to infrastructure, life gets much easier. Unfortunately, it's not practical. I'm an engineer. I like to build practical systems. Cheap, practical. Another question.
How do you take care of low lighting and bad weather situation? I mean, what do you need to do for that? So
how do you take care of low lighting, and I'm just going to say general environmental badness?
Yeah.
Sensor failure. There's lots of things that can happen. So some of the automotive-grade cameras actually have unbelievably good dynamic range. Really, really good. 20-bit effective. Okay? And they're grayscale. So I don't know if people have seen it. So usually people are used to seeing RGB cameras. Most automotive-grade cameras today, especially forward-facing, are what are called RCCC cameras. They have a red channel and then luminance for the other three. Extraordinarily high dynamic range, bizarre compression stuff, but you can actually get pretty good data. At nighttime, I'm not going to say it looks like daytime to the camera, but you can see obstacles quite well at nighttime. But the truth of the matter is, sort of I tried to say earlier, I don't think you would ever rely purely on an optical system. Fog, rain, sensor failure, right? So if you had radar ultrasonics combined with optical, and you're actually doing sensor fusion, either running neural network or computer vision on that, I think it provides the most robust, most practical system, right? I would love to be able to do everything optically, but you get dirt on the camera, right? You park under a tree and birds mess up your car. I mean, these are practical things that you have to live with. You drive in slush, right? There's practical things that you have to live with. And to be blunt, I mean, it's going to be a long time until everything you do is fully autonomous. Highway driving, we're basically almost there, autonomous highway driving, right? Even though you're at high speeds, the physics of things actually happen fairly slowly to you in the world. So you have time to react to systems. Are we going to be driving in snow? People think, well, snow, the problem is I just can't see the lane. No, your physics all change, right? Snow is hard. So like snow will be a while, right, to deal with. But, fair weather driving, highway, we're really close to being there. Even highway in the rain, I think we're going to be very close to being there. Without really super expensive sensors. Radar, camera, ultrasonics to detect the cars around you. I think we're awfully close. Another question.
Cars that can respond rapidly, right? They're very different copy image resolution. Have you guys got any concerns on vacant data?
Yeah, so we've tried multiple different types of cameras. So we have tried IR. Again, the neural network doesn't really care as long as you have tag data. Some people have tried IR cameras, especially to deal with nighttime. It's a little weird, though, because they blow out in ways you don't expect. So I don't know if people have ever driven down the Grapevine, coming back from LA, okay? Have you ever driven at night and actually driven by a truck? Have you noticed that all their brakes are glowing? Right? They're so hot. This is the problem with IR cameras. They see the engine, they see the exhaust. So you could potentially learn with it, but it has weird attributes. Color cameras, there's weird extended, really funny color cameras now. Again, if you can tag it, and that's really what's going in your neural network or your CV algorithm, yeah, you can learn on those. Our experience thus far is that neural networks are more robust to really weird signal setups, and they kind of figure out themselves how to kind of adjust to that if you have the right objective function in your training system. They're pretty robust. But usually we don't see that many weird things going to automotive. So grayscale, so RCCC cameras, RGB cameras. There's some people experimenting with RGBD, so depth, some time of flight stuff. All that actually fits fairly well into how neural networks naturally want to behave, right? Multi-channel, multimodal.
How much do you think this adds to the cost of the car? The hardware?
Yeah.
Software?
Right. So the cameras, the advantage of going to cameras, and then if you can offload a lot of the smart camera functionality, white balancing, image processing stuff into a central core, and the cameras get pretty darn cheap. Sub $100 per camera, really sub $100 per camera. Radar systems are still expensive. Very good radar systems are expensive. So, I mean, you're still talking, hundreds of dollars, probably $1,000 just in BOM cost for all the sensors you'd want on the car. And then you also have to have the computer, and then you have to have the software. So this is not like, a $1,000 thing. We're probably still talking, things that are going to be in thousands of dollars as an option, right? So the question is can we continue to push that to get safety up and drive the cost down? So the advantage of concentrating more on cameras than other solutions is cameras are getting cheaper way faster than the other solutions. Okay, but as I said, especially for high speed, in my gut, in the near term, I don't see getting rid of radar, of medium and long range radar for forward facing. All right. So let me quickly show you some of the things that we're working on and that other people are working on in the industry and research community. So we spent a lot of time on detectors. Again, that's just sort of table stakes, if you will. You have to have this in order to have your don't hit stuff functionality. You have to detect basic things around the world. So we've been doing a bunch of work on this. So this is a pure neural network approach. So people will probably recognize as a kiddie data set. Okay. So it's a good public data set. It's unfortunately really small to do really good neural network training, but you can test if you're kind of on the right approach. And so the goal here is to draw type bounding boxes around cars, pedestrians, bicycles, motorcycles, I forget all the classes. So we're able to actually train neural networks to do this. I'll discuss a little bit the algorithms later. But we spent a lot of time working on detectors. Obviously spent a lot of time on classifiers. This is one of my favorite examples because it's hard, and you can debate if we actually got this one wrong. Turns out we actually got this one right. Even though it's red, it actually is a police car. But it's, if you look at sort of, we're pretty sure it's a police car. It could be a fire truck, another good guess. But pickup also shows down there. I mean, they're way down the list in our confidence level. But just an interesting example. And then work on regression. So this is an example from the Deep Pose paper. So another form of training a network is what's called a regression. In this case, they're trying to learn the position. And there's pictures later, they just didn't have quite a pretty graph, that they can actually estimate the skeletal position. So how somebody's sitting, holding themselves in three-dimensional space from a two-dimensional picture. Pretty cool. Okay. And so we use things like this to begin like doing some forms of free space calculation, deal with actuator control. Those tend to be regression networks. So how do we do sort of our detection stuff? So it turns out, sort of back to our good old workhorse, AlexNet. So I'm going to go a little deep on you, and I'll point you at papers if you want to read more. But so that's what your ground truth looks like. As it turns out, you can actually abuse AlexNet, which has built sort of a very robust feature detector up front. And you can do a trick where you cause the effect of the neural network to scan that through. Okay? And what you'll see is in the lower levels of AlexNet, so around COM5, Pool 5, you'll actually see the heat map gets created. And that effectively tells you, you can figure out that a certain class that you're trying to find, car, happens to occur in this part of the image. Okay? So we call that a heat map technique. And it's one of these neat artifacts that we didn't just figure out on our own. Other people figured it out, and I'll show you the cool demo from Stanford that does this. But it's kind of this neat technique. So it's their same good old workhorse AlexNet.
So this is information heat, not thermal heat.
Correct, information heat. So I mean, there's a lot of argument of heat map is the right term, but that's what it looks like when you look at the visualization. You see this big spike that says there's a lot of energy right here from this class in the image. Okay, so we get a very coarse grid. So if you put all the pixels through, by the time you get to this heat map layer, you sort of get this very coarse grid. But you can see it sort of tells you, well, there's something here, something here, something here, something here, right? And the argument is that we actually don't have to draw bounding boxes. That probably for autonomous vehicles, that's all you really care about. This is your don't hit stuff. There's stuff here, right? And there's a car here. Like tight bounding boxes maybe don't matter, right? So, but from that, then we can actually run a regression and actually calculate from that heat map where the boxes are. So in this specific case, we're not perfect. We didn't get this car, but it's occluded. So do you really care for autonomous driving? That's actually one of my complaints about the kiddie data set. This car really matters in your score, but doesn't matter if you care about autonomous driving because you can't hit it. You can't get there. We also missed this car here. Same thing. Heavily occluded. You can see there's a box up there. Heavily occluded is actually on the other side of the street. So I would argue that in all practical cases, we got a good score. Not good enough to make top 10 on kiddie. So let me show you the cool Stanford stuff. So the Stanford guys took this all the way. So the red dots you're seeing are their estimate from the heat map. Then they generate the bounding box. They calculate time to collision. They don't have it on here, but they can also detect the lanes. This is all neural network as opposed to a computer vision approach. Why does that matter? So let's take the example of detecting lanes. Computer vision algorithms work amazingly well when you can see the lane. If you're on a country road where you have a soft shoulder, they begin to struggle. They may do okay if you have a center line, right, because it can kind of gauge. But if you're on a pure country road that has no line markings, we as humans do fine, right? But a computer vision algorithm has no point of reference to sort of set where its goals are, where the deep learning algorithms actually do really well here. So people in the Bay Area probably recognize where this is.
So what was the reason for it not recognizing some of those cars? Was it just a problem with the data set, or
So there's a couple of reasons. So this was very lightly trained, right? For a production system, you're thousands of hours of video. This one, I think they're less than 100 hours of video. So again, it's not perfect. The idea here is to show you how quickly you can actually get somewhere with these techniques, right?
Do we know that we can get perfect?
Nobody can get perfect. So, and I don't say that to be sort of snide about it, but you know, your single frame accuracy is never going to be that great. And so what you would actually do on this technique, as opposed to running a neural network every frame, is you would actually use a tracker, optical flow. You would help get false positives by calculating your ground plane, right? The only things you care about better be touching the ground plane, right? This is raw brute force, okay? So you combine all these techniques. Same thing, any production CV system, you know, that you have today, it's combining multiple techniques.
So if a plane comes down on the freeway, you're screwed.
If a plane comes down the freeway, I think you're kind of screwed regardless. Like your chance of avoiding that, so even a Cessna coming in is going to come in 120 miles an hour at you. I think that's going to be a tough one. Or, you know, have you all seen the thing, like all the crazy videos from Russia where like the tank suddenly comes in from the side of the road? No, I mean, there's nothing we can do about that. It's, your radar system comes on, try to stop it. Excellent question. So this is the question is you know, why are the red dots kind of shifting around? Why do they land where they are? So what the red dot is, so if we go back, the red dot is this heat map. So they've combined it together to say the activations that I'm seeing happen to be here. And so you'll notice in the video, especially on difficult aspect ratio things like the semi-truck, that by the way a lot of computer vision algorithms miss, it's beginning to shift around. And you can see, especially as it goes through shadow, you'll see it kind of gets noise in this oblong side. But again, and it actually got the side one too. So it sees a back and a side, it's tagged both of them. But the regression that learns how to put a box over it has learned to combine it. So you're basically seeing a visualization of multiple techniques happening at the same time in the neural network.
So did it know when it went around the corner?
No, it has no memory, if that's sort of what you mean. This is running every frame. This is not an RNN, really, this is not an LSTM. This is raw, detect.
I was just wondering, Tesla says they are going to do some software update and do some autopilot. What technologies are they going to use and not use that you have shown so far?
So what's Tesla going to turn on when they do autopiloting? Ask Tesla. This is just vision. This is just pure vision, okay? So again, I'm kind of showing you the hard stuff to demonstrate that can be done. Again, none of these are practical systems yet.
Frame by frame vision.
This is frame by frame vision. So how this was trained though is they actually used radar, and to get the lane markings, they actually used LiDAR, because LiDAR reacts with our fancy paint on California roads, actually most of the US in a certain way, so they can track it all.
This is on a bright sunny day.
This is on a bright sunny day.
What
Yes.
happens in the night?
Right. So again, at the nighttime, the high dynamic range, this is color cameras, because this was a GoPro. The high dynamic range cameras, you should take a look at one if you haven't seen them. So OmniVision, Aptina, they have these. If you actually look at them at nighttime, they have some blowout in them, but they're actually pretty good. I mean, you as a human can actually see that there's cars, and you can see the lane markings even at night. They're actually pretty impressive.
Certain vision company only made their algorithm uses a lot of the lower bumper of a vehicle for me. This is the car.
Yep.
And water spray on the street night, we almost it's unusable for
Yep.
any outdoor application. This production system.
Yep.
Are these algorithms more robust, given when you're looking at more broader parts of the environment?
So right. So the question is that there's some systems out there today that rely on very specific aspects of the car. License plates is actually the most common, but bumpers also. But license plates, because they're standardized in the U.S., they're a really, really good target to gauge distance. But if you have noise, water spray at night, right, where you can hardly see the car, those algorithms struggle. Does a deep learning algorithm do better? Yes and no. Okay. Deep learning algorithms tend to be better at reasoning under uncertainty, but whether or not you're going to get like a super accurate distance calculation, boy, really hard to tell. There's going to be noise in there. And again, anything you can do with a deep learning algorithm, you can pay 100 engineers to just beat away on a traditional CV algorithm and be competitive, right? It's just how fast you can turn around, how fast you can adapt. But all these are practical struggles, which again is why, in that specific case of road spray, why you would use a nice fancy radar system that would do target estimation for you, right? Time to collision, rough object size, distance, and then you would use that to supplement with your computer vision to get a better response. You had a question? This one's not using optical flow. Okay, there is no tracking here, which is one of the reasons that there's actually more jitter in the boxes than you'd expect. There's no common filters. This is raw. So optical flow, what optical flow does is it effectively calculates the pixel direction distance between two frames. So you can actually run it backwards optical flow, which will sort of tell you how pixels moved. And so you can think about it as sort of coarse segmentation under movement. Oh, so how do you get optical flow? So you can calculate it directly, or if you're actually encoding things with something like H.264, H.264 has a motion prediction algorithm that you can use as a poor man's optical flow. Other questions? Okay. Okay, so a bunch of paper links. Don't scramble to write them down. We'll post the slides. But lots of related work, or people can take pictures. Lots of related work here. Okay, everybody got the picture? All these things are Googleable, guys. Digital age, right? You can Google them now.
Michael, if you give me these slides, I'll put them on the event website.
Yeah, I'll make sure that we give all the links to all the interesting stuff. And so we have RSS triggers set up on archive, which is a really good thing to have, except it turns out they ban you. So if you have an RSS reader that's hitting archive too frequently, they'll actually ban you. But I recommend, and they're going to kill me for this, but I recommend that if you're interested in this stuff, is both deep learning and CV as the tags and archive. You can get notified of all the papers that come up. It's interesting to watch. There's a lot of really crazy research going on right now. All right, so let me show you something older. So this is not currently targeted for PX, but it shows you what you can do. So this is a very complicated network. I'll explain what it is, but let me explain what the structure of the network is. This is a combination of convolutional network and a multi-layer perceptron, sort of old school machine learning. And so what this is doing is per pixel segmentation. So it's trying to label every pixel the camera sees with what it is. It's not perfect because this was trained on like some random data set, so it has like sand and valley and stuff in it. And how they got this data is a guy riding a bicycle, put on a helmet with 3 cameras. Okay, so that's where the data is from. So you see the guy go through the park, don't freak out. It's not a car driving through the park. It is Boston. No, I take it back. It's New York. Yeah, so it's done by NYU. So as you can see, it's doing pretty darn well. So at the time, this was running on 10 frames per second on a low-end Intel chip. So on what we're capable of doing today, this would be actually faster than real time. And again, it's not perfect, but it's a good example of how far you can go. So if you really want to know everything around you that can be seen, this is about as far as you can go. I mean, no human can do this fast and tell you what every object is, every frame, for 270 degrees. And if you can, come work for us. You can help us label data. But again, it can kind of, he's riding through the park, and it's labeling, grass, and, it sees cars or there's not cars. Again, not perfect, limited data set, but it sort of shows you the types of things that can be done. So, and here's the related work that you can see. So that's the end of my slides. So my comment we get asked sort of a lot is, well, how do I play with this? So again, you know, we build and sell special equipment. You don't have to buy all that. Please buy it, but you don't have to buy that. So usually, honestly, how we tell people to get started is, you know, machine learning is pretty painful without a GPU, but all of our code runs on consumer GPUs. You can go to Fry's, go find, you know, GeForce 900 series. It can be low-end 950s, 960s. You can go all the way up to Titan X's, which are big memory, really, really fast boards, and you can run multiple of those. Download one of the frameworks. All the frameworks come with examples. Almost all of them come with sort of the hello world AlexNet, right? You can go download ImageNet, you can train these things, you begin to understand. Unless you actually play with neural networks, it's very hard to gain an intuition for why something's working or not working. Why is it overfitting? Why is it underfitting? What's wrong with my data? You know, nobody can give you a true answer for this. Nobody can offer you a tool that automatically does this right now. So you just kind of have to play with these things to understand. And all these frameworks, notably Caffe, Torch, and Theano, are all active research. So all the cool stuff going on in natural language processing, segmentation, detectors are all going in. So it's all available, and all of them have robust communities. So the best way to get started is, as I said, get a box with a GPU, download stuff, and get going. If you want a proxy, so if you're a startup, you don't have a lot of money, you don't want to buy, you know, dev boxes or PXs, you can actually take our really low-end GPUs and use that as a proxy. Okay, it's going to be faster than the PX, but somebody asked me this question earlier. If you kind of take one of our low-end Maxwell chips, so 950, 960, and you view that's like a factor of 2 faster, right? So if you develop your algorithms and you're off by a factor of 10, you have the wrong algorithm, right? If you're within a factor of 2, you're probably within the realm of being able to tune it down to the PX board. Also, the PX board, unlike its bigger siblings, supports 16-bit floating point. So it runs 16-bit floating point at twice the speed of 32-bit floating point. Turns out that for inference, not all, but a lot of algorithms can actually run a 16-bit floating point. So you get a big boost in performance. So you can shoot for a PC platform, you know, good old, you know, Linux desktop running Ubuntu, put a low-end GPU in it, and actually have a pretty good proxy for what you should be able to shoot for a PX platform. And then once you feel comfortable, come talk to us about getting a PX platform. We'll work it out. So that's all I have. I'm sure there's lots of questions. Well, front to back. Go ahead.
How soon is this going to be in cars?
How soon will things be in cars? Okay, so so you're actually beginning to see some of this go into test fleets now. Okay, so we have partnerships with various automotive companies. Audi has discussed their ZFast program, which actually combines Mobileye, a traditional computer vision ASIC, with our previous generation, the TEGRA K1. So that, you know, those are platforms where you'll start to see things being developed. There's multiple startups that are beginning to do things. When things go in cars and when you see this all on. So the honest truth is we're technologically very, very close to that. Regulatory-wise, we're further than that. And unfortunately, that's the frustration. So the goal and how everybody's sort of operating is you put these things in cars, you put it on test fleets, you begin building your data to prove what your statistics are. But you can see the sort of consumers' reactions to this. Like there's that sort of hit article on Google. It's like, oh my God, Google's had 4 accidents. Okay, everybody calm down. 2 of them weren't even their fault. They got hit. So those don't count. I mean, come on.
Like the fires in Tesla.
Right, it's like or the fires in Teslas, right? So these get blown out of proportion. But it sort of shows you the daunting problem here is that everybody expects that the computer is going to be so much better than a human. Right, I'd argue, I drive in every morning, the number of people texting on their phones on their way into work, please let autonomous vehicles come earlier, right? There's so many, you know, I mean, again, they're not big accidents, but, you know, a couple $1,000s in damage. Those would just stop happening. But this is about statistics. We need test fleets on the road. Statistics need to be gathered till regulatory insurance companies get comfortable, and then it begins to roll forward. As I said, you're already seeing this begin to happen. So people are talking about enabling autonomous piloting on highways. Again, sort of safe. Everybody's reasonably comfortable with that technologically right now. You let that go, you gather statistics. You move on to the next thing, perhaps urban driving, heavy traffic. So very constrained urban driving. And then maybe you deal with handling going through stoplights and making left turns. right? Fully general urban driving under all environments is daunting, okay? So that's going to take a while.
In that vein, just what was it that Mercedes Freightliner got approved for Nevada?
So Nevada and California right now are the easiest to get an autonomous driving license. You have to prove a bunch of things, but mainly you have to post a very large bond. But it's a lot of testing. And the way that most of these things work right now is there's always a driver with his hands on controls, right, going through this. Again, statistics gathering, improving you can do it. And unfortunately, that's just time and miles, right? I mean, I wish we could get to 1 million miles faster. That would be great.
I'm just curious about sensor fusion. Is
Sure.
sensor fusion done in another layer of the software stack, or is that actually a function that the neural network can perform?
Okay, so where does sensor fusion happen? And as usual, technical answer, it depends. So there's a couple of different ways to do it. So if you believe all the way in neural networks, we would say you fuse it in the neural network, right? You basically build a multi-channel data stack, right? So you have your image as one of the components that goes in the neural network, radar, ultrasonics, whatever that feeds in, and you let the neural network work it out. There's other things that are more likely, honestly, up front, which is better phrasing of it would be a sensor pipeline. So for example, one very rapid thing that you can do as kind of a quick demo to show off, if you have access to a radar system in a car, is use your radar system to provide you your initial object hit points. Right? Some radar systems will give you 64 no matter what. Right? They're not necessarily right. So now you can use AlexNet to now do your classification. So that becomes more of a pipeline. It's technically still fusion because you're using both of them together, but you've built a pipeline. Right? So there's a couple different ways to approach mixing all your sensors together. And there's no real right answer there.
You could take each sensor modality and process it with AlexNet and then combine them. I mean, there's all different kinds of ways to architect the processing.
Yeah, so you could do each independently and put it together. What makes me flinch about that is you probably replicated a bunch of computation so actually fusing them together either in a pipeline form, so sort of doing it as a filter as you go through, or truly fusing them and feeding them in a network, my gut is that's going to give you a better performance and lower power behavior on the car.
What's the sense of amount of memory required to store all the learned data for a particular car?
Okay. So good question, because this comes up a lot. So what does it take to store all the learned data in a car? Not much. So it turns out that AlexNet, 200 megs, uncompressed. Because what you've done is you've learned weights, so it's just floating point numbers. You have a lot of them, but they're just floating point numbers. The actual data, the petabytes of data you're going to have to train the system and validate the system, live on big backend servers. So that's why I said these become an over-the-air updatable type thing. I mean, 200 is a little big, but we can compress it, and we can get it down probably around 10 megs, or do partial updates because we're not updating the whole infrastructure. So it really becomes over the air. Now, would you do it over cellular? Maybe not. It might be too big. But maybe when you come home, sort of like how the bigger updates happen today on some cars with OTAs, then you'd take it over Wi-Fi. So they're not as large as you would think. There's a question right behind you. Right. So how stable is a signal? So in the real world, pretty stable. There's a big caveat, though. So there's something called adversarial images, which are fascinating. What the computer has learned is not how you and I see things. So you can actually take an image that you and I would still recognize as an ostrich, just to pick an example. You can perturb it a little bit, and the network will suddenly think it's a dog, right? But these are not natural things. What we've seen is that on true natural images that haven't been manipulated, that we tend to have pretty stable outputs. Now, a lot of it depends on really how truly stable you are and where your training is. If you're still flipping weights around a lot, then you really haven't settled down. And so you can get these weird sort of fall-off corner cases where it misclassifies. But again, this is why you continue to test and you continue to harden your networks. But yes, neural networks are susceptible to sort of these weird manufactured errors.
Michael, you want to take a couple more questions, and then we'll let people go
Sure.
to the next round of Q&A?
Another question, the last one.
Sure.
So the neural network helps you understand the content of things, like there's a board on the car. Does it know your
So, right, so can neural tell you the location? So yes, so when we're drawing bounding boxes, that's exactly what we're doing, is we're localizing the object in the scene. So we can calculate where that object is in space, right? So for example, a car, so I draw a bounding box, I know its rough aspect ratio, so I can calculate its distance if I know the properties of the camera. Pretty accurately, actually. I mean, not within 1%, but within 10%, you can do it. I'll take two more. Yeah.
How dependent is the training on things that are determined by your geography? So, for example, you said in the U.S., things are standardized. Does that throw a lot of the learning off in other regions?
Right. So the question is how region-specific is the training? It's region-specific, right? But one of the nice things about neural networks, and you have GPS in your car, we can swap modes. So you can load a different network. Loading a network is incredibly fast, actually, right? It's as fast as however you can read off your flash memory. But yeah, I mean, a good example is, so if you're doing lane detection, and all you've ever seen is people that drive on the right side of the road instead of the wrong side of the road, left side of the road, then it's going to throw off your detector. So if you're in a country that drives on the left side of the road, you are probably going to be running a different neural network. You'd also be running a different CV algorithm in general, right? So it's not a large difference there. But yes, you make it really, really hard on a neural network if you say this is a speed sign, and then you give it 1,000 different variants of a speed sign. You're much better off saying this is an American speed sign, this is European speed sign. Same thing with license plates. If you're using the license plate to calculate distance of a car, and you did it all in the US with our more squarish plates, and then you do that in Europe, you're going to have a very bad time, right? Because you're going to think the distance of the car is vastly different, right? Or you might not detect at all. So yes, there is some specificity that you'll do. Now, in theory, you can train the world's largest neural network. I just don't think that's a good strategy, right? You're going to try to define your architecture, and then you'll train region-specific. Same thing, it's like when we were doing our car detector, so somebody gave us video from Europe, and they said, well, how does your car detector work? Well, we had never seen a citron. They don't exist here. So we didn't know what it was, right? It wasn't in our data set, right? So these are the things that you run into. Your neural network's only as good as what your data set is. So it's one of the advantages and curses of neural networks.
How about the audio sensing? It's all video right now.
So how is audio sensing? So as I said in the beginning, most voice recognition systems that you guys interact with are neural networks, right? Again, neural networks are very robust under dealing with background noise, uncertainty, accents, things that are very difficult to deal with. So there's a startup, Capio. They've shown demos at GTC, but they're very close to what Google Voice is capable of, but they're running it actually locally without big back-end server infrastructure. And they can actually do it faster than real time. So we've come a very long way in voice recognition. Not solved. There's still issues. I don't know. I still fight occasionally with Google Voice. Get a funny little argument. Shut up. Stop. But yeah, I mean, voice, images, video tagging. Yeah, I mean, neural networks are being applied more and more. All right, one more in the back.
So in practice, when you're training these networks, what are the sort of things that you're tweaking? Are you actually going and tweaking the number of layers and the number of parallel layers having each layer, or
right? Right. So the question is when we design these networks, what are we tweaking? Yes, we tweak layers. Usually, we actually start with tweaking the number of filters in each layer, so the depth of each layer. So for example, AlexNet, the first layer, is 96 filters. If you have color, you probably need those filters. If you're doing black and white, I bet you can go to 64, right? So those are things that you tweak. I mean, again, a lot of this is about, you have to look at the statistics of how your learning is working, and then more importantly, when you start running activations through, you can look at your activation statistics. And one of the things that we look for to say if a layer is too big, it's if we run a lot of activations through, do we see a lot of dead filters? Filters that never respond. Okay, I've overbuilt my network. And that's usually our biggest fear, because we usually start overbuilding and then whittle them down. It's a harder question of whether or not you have enough layers. And so the way we end up thinking about that is if you find yourself usually you find yourself underfitting, then you've gotten yourself into a weird place. So you'll try shrinking or expanding layers. Same thing with overfitting. Usually if you have an overfitting problem, you have a data problem. We solve that by telling you to go get more data, right? But there's ways to do data augmentation, things like that. But it is an exploratory process. There is no magic here. And that's why I said we honestly really do start with AlexNet, VGG, GoogleNet as the places that we start, and we see if those are working for us, and then we adapt from there. We're out of time, but I'll be around.